All right, Robby, we're now live for your Inside Racket seminar. I'm just going to wait a little bit so we can have a few viewers join so we can make sure that not just you and I can hear the audio and look at the questions. Does that sound good?
Yep. Speaking of looking at questions, where do you look at questions?
If you go click over on the right, there's a little button that says Q&A. It's blue.
Ah, yeah, got it.
Normally, I just look at it.
That sounds good.
But you could look at it if you wanted. So we got 3 viewers now, so people are logging in. I'm just checking on Slack to see if someone can tell us if the audio sounds good and if they will ask a question. Normally, Sam asks the first question and he says first post.
Well done, Sam.
Yes. Very good. 6. Oh, now down to 4. Someone's having trouble. I feel like every time I use Google Hangouts, I'm being A/B tested. Do I slightly differently?
All right, so Matthew can hear the audio.
Okay. Staring at the screen, I just really love the graphic design on that blue box up there, that blue bubble. It's just so peaceful looking, and I love the gradient. It seems like just totally unnecessary to have a gradient, but it just looks so nice.
It didn't have a gradient originally, but then when the blue boxes, got when Butterick put in that wonderful improved version of our website, our documentation website, there was a gradient that appeared in the blue boxes there, so I copied it.
All right. Matthew asks, what is your favorite contract? So let's answer this question.
What is my favorite contract?
Yeah.
False.
False. That's a good one. I accidentally read this as, what is your favorite contact? And I'm thinking like, is this like bodily contact or like someone in my calendar and, in my phone? All right. So we've now verified that people can hear the audio, people can see your screen, we can add questions, so now we can start. So let me just remind everyone what the idea of the Inside Racket seminar is and what we'll be talking about today. The goal of the Inside Racket seminar is to really go deep inside of the implementation of a piece of Racket. And it's not so much to do a tutorial on that piece. For instance, today we won't be giving a tutorial on the Racket contract system. Instead, we're looking at exactly how these cool pieces of Racket are implemented so that other people can understand them in case they want to contribute, that they can be inspired to build similar things. And so we can kind of share the knowledge about building this kind of complex software. And in some ways, I feel like this is particularly good because a lot of the more interesting features of Racket are really only used for building the kind of language machinery that you don't use that you don't personally build on a day-to-day basis when you're building a programming language, but having that available to you when you're programming Racket is really valuable. So today we're going to have Robby Findler talk to us about the Racket contract system. So he'll, of course, explain a little bit about what that is, but this is really one of the crown jewels of Racket as far as I'm concerned. And in particular, it's one of the ways that we've had the most influence on the rest of the programming language landscape. You can look at many different programming languages now, and they're all touting their contract systems, which, of course, while contracts originate in languages like Eiffel, the modern notion of contract really comes from Robby's work in the early days of Racket. So Robby's going to be leading, and I'll be here asking questions. And take it away, Robby.
All right. Wow. I'm not turning red. I thought we'd start with some simple contracts and look at how they're implemented, and then move on to some more sophisticated, complex ones. And a good first one to get a feel for what a contract is and how the contract system is implemented is one that just checks whether some values a number and between a particular pair of other numbers, a real number and between a particular pair of real numbers.
Okay.
So that's called between C, and it's highlighted here on the screen. So this is the function. This define/final hyphen prop is effectively the same thing as define, but puts a little bit of information there at compile time that check syntax can pick up to tell you about obligations in your contracts. So
is this what like gives me the little bubbles?
Well, let's see, what is it to? So if I say contract out X between C1 and 2, so now I define X to be 1, then this should tell us that it's basically what added this thing here saying contract : this module's obligation.
Okay.
So that's pos prop. So it's a positive. Between C is known to be a contract combinator that has only positive blame associated with it.
Okay.
So if I were to write a function like this, then we would see now this tells us this between C is the client modules, and this one is this modules, and the fact that X has to be a function is, well, should have been showing up here.
Okay. And so, just to remind people of the contract lingo, positive is my fault, negative is your fault. If I am the one writing the thing that the contract is being applied to.
Right. And I'll say positive and negative sometimes when I should really say something a little bit nicer, and hopefully that doesn't leak out of the implementation too much.
Yeah, sometimes you say client and server.
Right.
All right, so we got
that's what define final prop does, is it puts information that turns into those little yellow things.
Okay.
So unfortunately, we don't have a contract system when we're implementing the contract system. So that's what this check between C is doing, is low-tech error checking for that X and Y are reals. And then we get to the interesting part, which is the construction of this record between C hyphen S for struct, I suppose. So the contract library is a big pile of combinators, basically. There's a little bit of extra code that's outside of the combinators that sort of gets you started to put, like that contract out that was in that untitled buffer 7 over there.
Yep.
But mostly the code is inside combinators. And most of the combinators are written as structs with, they're basically, using properties to do a low-tech object system. Okay. So there's structs like between C here, which has the low and the high, those X and Y arguments passed to between C. And then properties that all are functions that accept the particular contract, sort of like a this argument, and then do stuff.
Okay.
So, between C here is a flat contract. So we have the flat contract property. And
remind me, flat means basically like I can check it right now and never think about it again.
Yeah, right. There's sort of 3 layers to contracts. So contracts are values, you pass them around like anything else, and there's various predicates associated with them, and there's sort of 3 properties, I guess, that you could, the main 3 properties of a contract are whether or not it's flat, which means you can check it in totality right now when I ask you, and then it can just evaporate when it passes. Mm-hmm. Whether it's a chaperone contract, and then other, could an impersonator contract. Chaperone contracts have the invariant that when something passes
Maybe
in,
we'll go back to that when we look at what projections are.
Yeah. Okay. Yeah, we should. Yeah. But there's like the other 2 are both kind of residual. So when you put the contract on them, there's like still some code somewhere that's going to do something later on. Whereas flat contract, you can completely finish the checking up front.
Mm-hmm. And so the classic example of a non-flat contract is the function itself, because who knows what the function is going to do when you call it.
Exactly. So yeah, we'll see how far we get into the implementation of arrow, which is probably the most interesting non-flat contract to look at in terms of the implementation of the library.
Okay, so I imagine that there's tons of these flat contracts, which is why you have this build flat contract property function.
Yep. There are tons of them. In fact, every time you wrote a predicate, that just automatically gets coerced into a flat contract. Mm-hmm. So does false. So does everything else. Lots of other things like that. Mm-hmm. Okay, so between C, this build flat contract property is basically a record constructor, but where we have a keyword argument instead of by position arguments for the field, so that, because there's a lot of them, and a lot of times the defaults work fine.
Okay.
So in this case, we're supplying a name function. So it accepts the contract. So the CTC here is going to be an instance of the between C/S struct.
Yep.
And then in this case, because it's then, all generally accept the instance of the struct that they're on as the first argument. And then what they do with it, it depends on what the method is. So name here will return an S expression representing the name. So you can see it's doing things like between C is actually the same thing as less than equals /C, where the high end is positive infinity, or the low end is negative infinity. And so this between C and less than equals /C and greater than equals /C and equals /C are all actually going to build the same record as between C builds, but with infinities in the various places. And you can see that in the name here, how it gets returned back. And the reason that happens is because of stronger, which is the second method, I think probably worth talking about.
Okay.
So we still haven't gotten to any checking yet.
Yep. This is just making all those beautiful error messages.
Yeah, the name function is just about the beautiful error messages, right? Yeah, it's funny. I mean, the more I work on this thing, the more I realize what I'm really building is a DSL for error message generation. There's like so much thought goes into those messages. Okay, so stronger is a way of avoiding redundant contract checking.
Okay.
So if you have two contracts, one is stronger than the other, then you only need to check the stronger one.
Yeah, so this is like the classic weakening rule in logic.
Yep. So the stronger implementation is a binary method, and this is the definition for between C. So this, this is going to be a between C record, but you don't know that is going to be a between C record.
Yep.
So if it is, then you just check that the bounds are in the appropriate way. Mm-hmm. And there's another case, and this is the usual thing with binary method problem, is filling out that square can be kind of annoying.
Yeah.
So here's a case for handling one of the other contracts that happens to be in this file. And between C, it just asks you to to make a good effort. So you can always return false, even if it might be stronger. That's
So this is sort of, going back to that, it's just a little object system.
Yeah.
Because what we're really seeing here is like a multi-method, right? And so when I make my own contract, I can't tell between C that between C is stronger than it in certain circumstances, because we just don't have the ability to do that.
That's right.
So basically, like, even though I may want to like open up a lambda and my little check that's like between C, there's a huge amount of value in using the combinators that the Racket contract system provides, so I can get this nice stronger behavior, for instance, that you've made.
Exactly. Yeah. And yeah, there's lots of, I don't know that we need to spend too much time on between C, just to show you that that's one other method that, I mean, on stronger, just to show you that's one other method that exists there.
Okay.
But while there is a bunch of smarts built into the way stronger ends up being called, so it works correctly with recursive contracts. And it has some special checking for OR built into it, because when you're doing OR, you really care to be dispatching on the right-hand side rather than the left-hand side.
Yep.
So it's got a few smarts built in, but basically anyway. So, okay, so then first order. So every contract comes with a predicate that tells you, does this pass, does this not fail immediately, roughly?
Okay.
So in other words, even when a contract is not a flat contract, there are still properties that parts of the contract you can check immediately.
Like procedure, huh?
For example. Yeah. If you have a function contract and you know the function, like you wrote arrow, integer, then you know that's got to be an arity1 function. So you can check that much of the contract immediately. So that's what the first order predicate is about. In the case of a flat contract, the first order check is the entire check.
Okay.
So we can see what this is doing here. It's just, and again, we get the contract in as the first argument, and then we return a predicate. And so this predicate should be total and should return true in the case of a flat contract only when the contract passes, and false otherwise.
Okay.
In the case of a non-flat contract, it might defer some checking. That would be separate. Okay. So that's basically where this is the entire checking for the between C contract, this little and here.
Yeah, and if I wasn't using the combinator, that's what I would write, but I would forget to write real, huh?
Right. That's believable. Yep. I've not done that many times. So then one of the default arguments here is something called a projection. So this build flat contract property has a bunch of other arguments that we're not passing here. And one of them is the projection, and the default argument for the projection, which is the code that actually does the checking that's invoked by something like contract out. In the case of a flat contract, it just calls the first order check.
Okay.
So the default value is doing that here. And then the final one is the generator. So contracts all come with the ability to both generate and test values. So if you have a contract, you can ask the contract, please make up a random value that satisfies you. And the contract will generally oblige with that. So like contract random generate between C and 2 says, okay, 1, 2, 1, 2, 1.5. So that's what this code was doing.
So that's like, quick check.
Right.
That's built into the contracts, but because quick check is based on types and we don't have types, contracts sort of serve the same purpose.
Right. In quick check, you actually write your own generators, generally speaking. But so you can think of this as like the contract system comes with a bunch of built-in generators for a quick check like thing.
Okay, cool.
And so this is the generator here. So usual kind of like, let's do something that seems to be interesting.
Yeah, these numbers seems like you probably put a lot of thought into them. That's not worth talking about.
Yeah, maybe not that much thought, but yeah, I'm going to agree it's not worth talking about. Yeah.
Okay.
It's fun to play around with making random things. So that's basically a combinator. That's the shape of a combinator.
Okay, so it really isn't that painful to add a totally new one.
Right.
Like this.
Right. And there's a little bit of benefit to it when there's structure to it beyond just some predicate you've written. So if you just write a predicate, you can just drop that in anywhere where our contract is expected, and that predicate will be automatically coerced into something that looks like this, except for it won't be able to generate random ones, and it won't have a stronger function, or it'll have a very naive stronger function, just basically EQ.
Okay.
So if there's some value, like in doing generation for testing, or you can then build something like this.
Okay. All right. So I feel like I know, about a simple flat contract. Can we go look at a slightly more complicated one?
Yeah.
Either flat or not flat.
Let's look at a not flat one. So this is box C. So this is a variation on that other.
That define final prop thing.
Yeah, exactly. So this one is saying that. So this is the immutable box C, right? And it's saying its argument is also a contract, and its argument is a contract that's in server position, positive position. So whatever position the box is in, whoever's responsibility it is to come up with a box, it's also their responsibility to come up with the right contents of the box in the case that the box is immutable.
Okay.
And the constructor for boxes in general, which is down here, kind of rolls its own version of this. So this is a macro that's just basically inserting properties and then expanding into box C proc. And the reason it rolls its own is that the argument to a box C is in both negative and positive position. Because if you mutate it, you're sending something sort of back from the client to the server. If the client does the mutation, and if the server does the mutation, it's sending it forwards. So it's sort of the streams cross there. So that's
and the pain that I see in this macro implementation is because, yet again, in the same way that the contract system can't use contracts, you can't use syntax parse because syntax parse uses contracts.
Right. In fact, syntax parse uses like Racket contract base, I believe, of which this is a part. So some parts of the contract system use syntax parse, but unfortunately not this part.
Okay. All right, so the real work happens in this box C proc.
Yeah. So a box C contract has the contract on the contents of the box, and you can give it a contract that's different for writing and for reading. So that's what this optional LMR argument is. The defaults to the same as LMW.
Okay.
You can also insist that the box is immutable or isn't immutable, or you don't care if it's immutable or not, and it defaults to immutable or immutable boxes are both okay.
Okay.
And then you can also ask, this flat flag is a shameful part of the past of the box C contract, I would say.
Okay.
But basically you can get, for many of the mutable contracts in the Racket contract library, you can get a contract that says, oh, it's mutable, but I'm just going to check it right now. And then I'm not going to, and I'm going to give you back a box that's still EQ to your original box, but I won't check on future mutations.
So it basically is only checking the positive side.
Yeah, and also not checking, like if the server decides to mutate it later on.
So it's not even only it really is flat.
Okay, yeah, it really is flat.
Okay,
it really is flat.
And you implied before that we never want this, but it's there for backwards compatibility. Is that something? Is that?
Yeah, I think that's a fair statement. I think the box C contract predates Chaperones is the issue. So we didn't understand how to do it properly, and yet we still wanted to have boxes in our contracts. And so we did something we knew how to do.
Okay.
So we can skip over this make flat box C and just look at the Chaperone box C.
Okay.
So here it is. So this is a struct that has, I didn't mention this line here, but every contract has, I should say, this line in it, which just makes the contract print nicely.
Yep.
So here's the name, here's the first order check, and stronger function, and then which are all probably, as you'd expect, we get into the reason we look at boxes at all is to look at the projection argument.
Yeah, totally.
So maybe the best place to look is the docs quickly here for this. Okay. So there's a little bit of history here that mostly we don't have to worry about anymore, but this late neg proj valve. Oh, can you guys see the docs?
No, we can't see the docs. We just see Dr. Racket.
Okay, because the thing is not.
Did you select only? Okay, there you go.
Okay, so you see this leg proj, val first proj, and get projection arguments?
Yep.
Get projection is the original, and the one that people sort of gravitate to, I think, when they first try to write new contract combinators. And it's the simplest, so I'll start there. And then that one anymore, but it's there for backwards compatibility. So function, just like these other ones, like the name function. So you get the actual contract struct in as the first argument. And then you get, what you should return is a function that accepts a blame object. Blame objects give you information about how they're basically stuck into the error message at the end. Okay. So they include original parties and what path we are through the contract. So if you think you have a box C, of a box C, of a list, of a function, of a whatever, the blame record is going to have through that tree to the particular contract, which then gets turned into something in the error message.
Like, and then uniquely identifies the border, right, between the two modules, which is why this is curried, so that you can kind of only make it one time for every border.
Yeah. Oh, yes. It has the names of the client and the server modules, or if you're using contract out, it's always going to be two modules. But if you're using define/contract, it might be some other more fine-grained thing.
Yep.
But in addition to having the names of the two parties to the contract, it actually has path information about what combinators were used to build up this contract.
Okay.
And there's a few other things it has in there. But the right way to think about it is that's all information. You have to just remember that thing and then hand it off to the function that actually raises the contract violation, and then you get a nice error message. And that's got all the information in it to build that nice error message.
Okay.
Okay. So as a combinator, you have to contribute to that error message building, and then you use it. So combinators have to say, I am the box combinator, and I'm now handing it off to the contract that's in my argument for recur through that structure here with this. All right, and then after you get the blame object, you should return a projection function. So this is a function that accepts anything and returns anything, except what it returns should obey the contract. or to put another way, what it returns is guaranteed to obey the contract.
Or error.
Right. And the way that, right. So if it doesn't return at all, that sort of counts.
Yep. Classic, type theory judo.
Exactly. So that's kind of the more straightforward one. This doesn't work very well for performance reasons. And that's why we have these other two variations. So
Okay.
latent egg is the ones, don't bother with val first, basically. That was an attempt that was just dumb.
Okay.
Which it took me a while. It's basically the same as latent egg, except with an extra curry, which is dumb. All right. So the latent egg projection has these same first two things. So you give it a contract and a blame object. But this blame object is slightly different than the one that we talked about before, because it doesn't have the name of the negative party yet. It has all the other information, but just not the name of who's the negative party.
Okay.
And the value of that is that you can, on the server side, lots of information about what the contract violations are going to be without knowing who the client is going to be yet. So you can do all that work only once and then just use it for every, because like when you provide something, it gets required presumably more than once.
Yeah.
So you do a bunch of this work on the server side.
Okay.
And the one piece of information you don't get is the name of the client module. So the blame object contains all that other stuff that I was talking, this path into the contracts, and it's got a bunch of nice things. And it's missing that one, it's basically missing that one name. And that's what that extra argument is to the projection.
Okay, so just to understand, so like with the get projection, like where it says blame, I'm going to think of that as being blame pause plus neg. And then when I look at latent egg, I have blame just pause, and then that first NEC is blame neg. And so now I have the blame neg, and I can combine them back into what get projection originally got, which was both of them together.
Yes, exactly.
And that,
except it might be the other order of those arguments, but yes.
Okay, and that is better for performance?
Yeah, it's better for performance because I can build the blame object on the server side.
Okay, so there's like less allocation or smaller allocations?
Right, less allocation. So if you have higher order functions, if you have functions at least second order, it's probably makes it worse because you have to deal with this extra layer of passing things around.
Yep.
But most of the contracts are first order. In that case, it's better.
Okay, interesting.
Yeah. Okay, so latent egg projections are what we're going to be looking at here. And there's a way to go back and forth between blame objects that don't have the negative party. You can combine a blame object and a separate negative party into a blame object with a neg party.
I imagine there's just a little algebra of them.
Yeah, exactly. So we try to avoid using that little algebra, but when there are projections that don't have a latent egg projection, when there are contracts that don't have a latent egg projection, then that little algebra happens in order to call the get projection method of some of those older contracts. They're mostly gone now, but there's a few still out there in the wild.
So even though the type is more complicated and it's newer, like we really shouldn't be scared of using to write a latent egg projection as a get projection.
Right. You shouldn't be scared of latent egg projection. You just use it. Yeah.
Okay.
I lost you briefly in the middle there.
Yeah, I mean, even someone like myself who's basically afraid of nothing, when I look at the contract documentation, I've always leaned away from latent egg projection because I figured, this is advanced stuff that just Robby needs to know about. I just use the basic get projection, and now I realize I've been thinking about it wrong.
Afraid of nothing. That's good. I want to be that someday. All right. So this thing then is one of those. So HO latent egg projections result is one of those latent egg projections.
Okay.
And its argument is either chaperone box or impersonate box. Right. So now maybe it's time to talk about the difference between chaperone and impersonate contracts. We talked earlier about what flat contracts are. The other two categories are chaperone contracts and then a catch-all, which is impersonate contracts. Chaperone contracts have the invariant that when you pass in, say, a box to this projection argument, that any arrow any at the very end there, you're going to get a box back.
Mm-hmm.
So they have this invariant that the thing you pass in is going to behave the same, except possible errors. So they can't be used to do coercions, for example.
So I can't turn a box into, a lambda that, has this weird functional interface to boxing.
Right. You could do that with an impersonator contract, but you cannot do that with a chaperone contract.
Okay. And that's good, presumably, for like typed rackets type system?
Yeah, it's good. Really, the goodness, I think, comes from finding a nice place to break the to separate out the runtime system from the contract system implementation. So there's some things that have to be in the runtime system, for performance reasons or for sort of undue power reasons. That the contract system is a library, and so it needs some support to interpose on things. So it needs to interpose on functions being called. It needs to interpose on boxes being mutated. Stuff like that.
Okay. So for instance, when I call setbox, like the contract system didn't implement setbox. And so
exactly.
How is it that we're going to catch that setbox and use our write thing?
Exactly.
So there has to be some interface to let it call some other code right before it does that.
Exactly. So it's this function. This function, chaperone box. So if you say, chaperone box is part of the runtime system, and it's the interposition hook that the runtime system is willing of us, those of us who are like not in the runtime system and not in the FFI.
Mm-hmm.
So it gives you a way to interpose on, in other words, to put callbacks in at things like when mutations are happening to boxes or when boxes are being dereferenced,
mm-hmm.
without giving you too much power to do sort of arbitrary things.
And so this whole problem wouldn't really make sense to, say, a Java programmer, because they would just say, well, isn't box just an interface, and shouldn't the contract system just implement a contracted box that that satisfies that interface? But that's not how Racket works, and so we need this other way of doing it.
Yeah, that, and I think that when you say box as a concept in your programming language, there's certain expectations that you have with it.
Mm-hmm.
And those expectations, that it behaves like a box. You can stick stuff in it and get stuff back out later, and what you put in is what you get out if you didn't share it with somebody else,
mm-hmm.
who then created a separate thread and it's mutating it in parallel to you. Mm-hmm. Then you sort of, you know something about the behavior of this object, and you can reason about the behavior of your program. And so the design of chaperones is intended to let the contract system be implementable outside of the runtime system, and mm-hmm. while at the same time not breaking all of our understanding of how the semantics of boxes work.
Okay, yeah. That makes sense.
So chaperone box, you give it a box, and you give it these unbox proc and set proc, and basically those are called whenever the box is mutated or looked up.
Okay. And so basically this code is going to be exactly the same for chaperones or impersonators, and so that's why you've just parameterized it over these. So basically we're going to, when we look at HO latent egg projection, we're going to see it call this function and give it it's basically going to make these unbox proc and set proc.
That's right. That's right.
So can we go into see those before we talk about impersonators and what makes them different?
Yep. Okay, so we get the contracts that correspond to the write and read contracts that we stashed in the struct. That's what these first things are doing. We
mm-hmm.
determine if it's supposed to be immutable or not. So we collect a bunch of information about the contract that we're going to care about for actually checking it. So in general, these functions are curried in such that you can compute a bunch of stuff. In this case, just a bunch of field selections.
Mm-hmm.
Before you go on to the next level of the currying, roughly. So we can get out some information when we have only the contract. Then we can get out we get a little more information once we have the blame object. And then here we get the value and the name of the negative party. And now we can start to do some contract check.
Yeah, and each of those things at the blame level, lines 139 through 141, those are the allocations that you were talking about.
Yeah, exactly. Okay. So this add box context, that's a function that just makes a note on the resulting blame object will now say the contract inside the box was violated.
Yeah.
Whereas if you pass this blame object, it will say it wasn't a box. And then if you pass this box blame, it's going to say it wasn't a whatever thing is inside the box.
Mm-hmm.
Yeah.
Okay.
Okay, so
I like it how your suffixes have the wrong thing. VFP for value first projection.
yeah,
We're doing a little bit of archaeology.
right. Yes.
All right,
so this blame swap will change the positive and negative parties.
mm-hmm.
And then here we end up with the projection for the negative, and here we end up with the projection for the positive.
Yep.
And here's the call to the chaperone or impersonate box. There's our value. Here's the unbox proc.
Mm-hmm.
So this gets called with the box and the value. And now we do know that somebody just opened the box. So now we want to check and see whether the thing inside the box satisfies the contract before we actually return it.
Okay.
And so that's what pos lmr proj does. So we're just calling the projection for the contract inside us, basically.
Okay.
And we checked to make sure that val was a box.
Yep.
Yeah.
And if everything was immutable, then we never needed to. We didn't need to return the chaperone. We could return an honest to goodness box.
Yeah. This is another thing that's a concession to backwards compatibility here. So it actually copies the box if it's an immutable box. That's what's happening.
Rather than checking it and returning.
Well, it copies it and then so it creates a new box.
Mm-hmm. But the contents could have been projected.
Exactly.
Yes. Okay, that makes sense.
Exactly. So we know we need only the positive projection here because it's an immutable box, so it can't be mutated. So there's not going to be any blame associated with the negative projection, with the other side of the projection.
Yep.
But in my opinion, if we'd sort of done this a little bit differently, does the projection copy the box would be a property of the entire projection and not a property that we're checking so late that involves the value itself.
I see.
But that's sort of a backward compatibility concession here.
Okay.
It doesn't seem to have caused anyone any trouble. But.
Okay. So I kind of have like a stack of 3 things that I'm curious about here, but I don't want to.
Go.
Okay, so we got to get back to what makes the impersonators any different.
Yep.
I'm really curious about this with contract continuation mark.
Yep.
And I'm very curious about these properties at the end here that are based on impersonators. It says contracted and blame. So which of those 3 things is the best one to talk about now?
Let's talk about with contract continuation mark.
Okay.
Okay. So
I love continuation marks. So I mean, my eyes just like lit up when I saw this.
As part of his contract profiler.
Okay.
So we're creating, so with contract continuation mark is just with continuation mark with a particular key. And the key is hidden off somewhere.
Okay.
This is the value. Blame plus neg party is going to be the value of that key.
Mm-hmm.
And then this is the sub-expression of with continuation mark.
Okay. Now, let me just recall for people following along. Continuation marks are a way of, the one way you can think about it is that they're a way of storing information in the continuation so that like the dynamic context of this set of parentheses, this highlighted code, can go back and look and see what was that contract that I got before, and it will be able to read off this blame plus neg party. It won't be able to, and it'll just get that value which was constructed here. And so one way you can think about implementing this would be like storing information in the stack and having the ability to walk back and look at the stack. So with that in mind, why are you storing this? I mean, you said it's for the contract profiler, but like, why is that useful?
So the contract profiler will occasionally sample. So it'll take the thread and say, please, you're running some program thread that's running your program that you're trying to profile. Please tell me everything that's in a continuation mark in the current context of that this thread is executing in that has the contract continuation mark key.
Okay.
And so you get basically a list of these blame plus neg parties back.
So that's going to tell us right now which contracts are being checked.
Exactly.
Okay.
Also tell us whether there's a contract, whether we're actually checking a contract at the moment.
Okay, because once the value comes out, that thing's gone because we're just marking the continuation. We're not marking the value.
Right.
Okay.
So it's a way to find out if you're spending a lot of your time doing contract checking in some program.
Okay.
And more importantly, because you can just turn off contracts and then you'll find out if you're spending a lot of time doing that. But you can find out which ones are the ones that are mattering.
Mm-hmm. Although
so
it turns out that you can't really turn off contracts, but we can talk about that later.
Well, okay. You can use a low-tech method to turn off contracts, is what I was thinking. Yes, it's not the contract library itself doesn't give you a hook for that. But if you these blame objects contain the names of the contracts. So they, we were talking about this earlier. How if it's a function that consumes a box that must contain a list that has Booleans in it or something like that, then that tree of the fact that I'm checking the Boolean part right now has the blame object will have the entire tree there, so you can find out what your hot contracts are basically.
And why doesn't it use box blame? Why does it do blame? Because the box blame is already part of pause element r proj?
Maybe it should use box blame.
Okay, so there's not that.
Think about that.
Okay, all right, so that was thing number one. So the other two things was, what's the deal with these properties down here, and what makes the impersonators different?
Okay, the properties. So it says impersonator prop, and that's because chaperones are impersonators, and so all properties are impersonator properties. So let's go back to I don't know if you remember now, but here, if we look at the signature of chaperone box again.
Yep. So I presume that impersonator box is going to have exactly the same contract.
Almost the same. That's the impersonator box one.
Okay.
But they both have this prop thing.
Yep.
So both chaperone box and impersonate box give you back a new box, and the new box that they return will call the unbox proc and set proc, not the original box.
Yep.
So one of the other just like happy features that impersonators and chaperones give you is the ability to stick properties on that result and then ask for them later.
Okay.
So you're just passing in key values basically, which then get sort of stashed in this extra record that gets created.
Okay.
And so what we're doing here is we're stashing the contract and the blame information.
Okay. And so, I mean, I can sort of understand why those might be useful, so I can sort of figure out later what was there. But I mean, isn't that the whole, like, the only reason I can think of needing this is because I'm going to throw an error message. But the error message already knows what the contract is and what the blame is. So what's the purpose of putting these properties there?
We have a minute for a little demo, maybe?
Yeah, sure.
So let's say I write this function.
Yep.
Which is, what am I doing here? Oh, yeah. Get rid of this part. Okay, so let's see. Let's call this this. Let's do it this way. So this is a false contract.
Okay.
It's
because
saying
like -1 gives us a complex number.
Right. Exactly. So if we say, I think, can I do this? Yeah. We can say, please try to break this contract. Contract exercise will say, oh, you give contract exercise a value that has a contract on it. Mm-hmm. So inside arrow, just like inside box, there's that same impersonator property thing that's sticking that same contract on there. Mm-hmm. And what contract exercise does is it takes the contract off and uses it to do some random testing. So in this case, what it did was it made up some random numbers, passed them in, and see if f always returns a real. Okay. So that's the main use, I think, of that property right now, is that you can pass values that have that property contract exercise. But in general, what it does is it's the way that value contract is implemented. Okay. The value contract looks at that property.
Okay, and so you might think that like if you were thinking about Haskell or Java or something like that, you might think that these contracts are like stored in the syntax somewhere, and so this is weird. We're like taking the syntax and putting it in the object, but no, they were runtime the entire time.
Right.
So all we're doing is we're saving something from when an object was created, so that it follows it along for when it's eventually used, so you can get back that information that helped make the value.
Exactly. So this blue highlighted expression here is an expression position, and you can write any program you want. So arrow is really operating essentially like a function here, and accepting two numbers these two predicates as its arguments. So the whole contract library has this flavor to it, that everything is just combinators and they're all expressions, and you can write your own library on top of them and abstract over them. And there's more to say about this. Check out our ICFP paper, I think is the thing.
Okay. So, the premature optimizationist in me is nervous about this giant contract going around, following all these objects around. Should I be worried about that?
I think we could all do with a little less worry in our lives.
Well, I did tell you that I'm not scared of anything, so I guess I shouldn't worry too much.
Yeah. I think that if someone were to do an experiment to discover that there's undue cost associated with this, then I'd find another way to do it, or stop doing it. So in other words, I'm lacking a measurement that demonstrates a problem. And those measurements can be pretty illuminating when it goes to fixing problems anyway. So that's why I wait for them.
Okay, cool. And then the blame property is similar. Yeah,
that one's less immediately useful in this. I don't have as cool a demo over that one, but you can ask, here's a value. Please tell me who's going to be blamed. What's the blame object that's associated with this value, with the contract that's attached to this value?
Yeah, who would be at fault if this were bad? But you don't have a good example of why I want that. But you can assure me that there is one.
Yeah, it's really going to tell you who were the original parties that were party to the contract that's on that value.
In case it's gone off to some third context.
Yeah, you can. It's like meta information that I imagine an ID might use, or other things like that, for which I don't have something cool to show you at the moment.
Okay. And so going back to impersonators for a moment, why do we ever want impersonators? Your example of why chaperones are good just seems so thorough. Of course, chaperones are the correct behavior. How could you ever want anything else?
I don't have a fully formed answer to that, but the reason why we even have impersonators to start with is to support parametric polymorphic contracts. So the thought there was that one way you can get a sort of dynamic version of parametric polymorphism is to do something sort of like what Morris talked about, as a way of doing abstraction in Lisp-like languages, where essentially what you do is you wrap objects in some opaque container, and then no one can really do anything with it anyway, except possibly give it back to you later, or choose not to give it back to you later. So it sort of has the same spirit as Reynolds parametricity does, but in a dynamic way. And so we experimented with that in the contract system. And so there's a contract which essentially has a projection like this, but it doesn't return a value that is the same as the value, as the input value. It returns a value that's wrapped in one of these opaque wrappers that you can't get back anymore. Okay. So you can imagine like a parametric polymorphic identity function, or a function being forced to be a parametric polymorphic identity function, or something like an identity function, by always wrapping it in these wrappers that it doesn't have the selector for before its arguments in the wrappers like that before you pass it in to you, or I don't know, maybe it could stash it and return an earlier argument or something like that. But it's really limited in a similar kind of a way. Yeah.
So to sort of think about a general principle, like one way that people think about contract systems is that contracts are dynamic enforcement for static types. Like any static type that exists, you should be able to construct a dynamic enforcement for that too, and vice versa. It's sort of like advances in static typing sort of push us to try to create better contracts, and advances in contract create better static typing. And so since static types already have this parametric polymorphism, this is an attempt to recreate that invariant on the dynamic side.
Yeah. I mean, there's a lot more to contracts than sort of mirroring types, but I think that there's value in looking at the two as inspirations for the other, for sure.
Yeah. Okay. And so really, that's the use case. That's the main use case of impersonators.
Yeah, that's the one that drove us actually implementing impersonators and supporting them in the contract system and things like that. Is this attempt to do parametric polymorphism?
Do you know if there are any weird use cases for impersonators that were found out afterwards? You know what I mean? This is the reason you made it, but it turns out that it's really good for making this other thing.
in the paper that we wrote about them, we looked at a few other kind of people like to interpose for these various other reasons, and how that would work in with chaperones and impersonators. But
nothing exciting.
I wouldn't. Yeah, well, I don't know. I mean, but I wouldn't say that someone has come along. I don't know of anybody that's come along afterwards and be like, "Oh, I can now do my awesome thing." Maybe just because I haven't been paying enough attention that I've missed it. But.
Okay. All right. So, is there anything more to say about the box, or shall we move on to something even more complicated than this?
Yeah, we can move on.
I mean,
the impersonator thing. Yeah, the reason it's abstracted over a chaperone and impersonate box is because the contract inside the box might be an impersonator. The box projection itself never adds any impersonatoriness to it. Mm-hmm. But if you have a box that has one of these polymorphic things inside it, then the box itself is going to kind of get infected in that sense. So that's why we actually have to use them here, and that's why throughout the library there's going to be a lot of chaperone / impersonate hyphen
whatever. Mm-hmm. Okay.
Yeah. Okay. So functions.
Yep.
Okay. So
my assumption, by the way, is that like I don't know, maybe like 15% of the library is some sort of basic combinators. Then like another 15% is like all the flat contracts, and then everything else is arrows.
I wouldn't disagree with that, but I have no idea if it's true.
Okay.
Could be reasonable. I didn't, I don't know. There's a lot to the arrows. I can agree with that.
Okay.
And there's a lot to them partially because Racket has interesting functions, and partially because there's a lot of special cases in the opportunities for optimization and the implementation.
Okay.
So.
Yeah, because I mean, like, I can write down in 10 lines a really stupid projection for functions, right?
Yes, you could.
And so, would you mind just writing that down real fast? And so we can sort of see, like, this is what you could do, and we're going to specifically do something that isn't that.
So, for example,
don't even do the arity. I mean,
okay. So, yeah.
I was going to have you do apply.
Something like this, where we're going to put a little bit of extra. I don't know. We'll do a little extra checking here, and then we'll do a little extra checking here. So if you add in some checking here and you add in some checking here, this is the we put raise blame error name here, something like that.
Yep.
This is look at that, 9 lines. This is the dumb one that you were talking about for like of course we don't want to do this because this won't be a chaperone. Mm-hmm. So that's another advantage of chaperones I didn't really mention, but they support equality. So the equality function knows how to recur through chaperones and can tell you if you have 2 things from the same chaperone. There's this function called chaperone of, which forms the basis for an equality procedure that can sort of say, oh yes, these are the same box in the sense that if you mutate one, the other one will change, and etc.
Mm-hmm. So basically, like, thinking about this as a little bit of a prototype, we're about to go into the depths, and we're going to basically see how each idea here shows up there, but deals with all sorts of things that you didn't think about when you wrote these 9 lines, as you were saying, oh, contracts are easy.
Yeah.
So just as an example, in preparation for this, I went and looked at a JavaScript contract library, and this is basically what they do for their function definition, for their function contract. And so from this point on, there's a lot of advice to be given to other contract implementers.
Okay, sure.
I can say that, Robby can't, I guess. Robby is too humble. All right, let's go check it out.
Oh, it's a false humility. So, but one thing to point out already that we talked about is that you can't just do this, so you have to do this. Right. Mm-hmm. And the chaperone, so you have to put something here. So the chaperone procedure, it's perhaps worth spending a couple of minutes on what chaperone procedure, I don't know, maybe we want to come back to this in a minute, but chaperone procedure, you don't write the wrapper function directly because then the chaperone the runtime system couldn't maintain its invariance about making sure that you don't monkey with the function.
Yeah.
So what you supply here is you supply a function, and then you supply another function that takes the argument and does whatever argument checking, and then returns the argument, or possibly with its own chaperones, and then returns another function where you do the range checking. So this is actually kind of what the 9-line version looks like, with a chaperone call in it. Kind of has this shape. So function chaperones, you give it a function, and you have to give it another function that has the same arity or more, or richer arity. And that function should return n results
plus one
for
more
each of the arguments that you actually got. So if this was a lambda args and you happen to get 3 actual arguments, you should return 3 results. And then optionally plus 1 result, which is then used to interpose on the function's result itself.
And this, this facilitates a dependent contract.
Right, because you can talk about x inside these ellipses, for example.
Yeah, okay.
One other thing worth pointing out here is that you can only do this if you know for sure the function is going to return 1 result.
So that's yet another thing that you got to worry about. Right.
And in general, the function, you don't know how many results it's going to return, so you have to really write something like this. This is where you would put the sort of good case checking, and something like this is where you would call raise blame error, the function return the wrong number of results.
Okay.
So this is the kind of shape that we're going to be looking for. And let's see. One more thing to say before we go back to the code. Most of the code is actually just chopping up and building the blue stuff.
Okay.
Here. So it has to build the part that does the argument checking, and it's going to build that separately from the part that does the result checking, and then it's going to, and because there's very special cases in those two things, and then it's going to combine those two together.
Okay.
And the goal is to really avoid writing this.
Yes.
But we don't want to require the runtime system to allocate a list of arguments when we know that the function is only supposed to accept 1 argument. So you could write a kind of dynamic, well, I think dynamic arrow in star, if we were to dig into that, does this. But really a lot of the work here is really just to make sure when it's safe to, we put this thing in instead of putting args, lambda args and, car or whatever.
And so, and one way you could think about that is that going back to the point that the contract system is a library, it's not like part of Racket, like the compiler doesn't know anything about it. So if every time you use contracts, it turned a single arity function into a variable arity function, you'd basically be destroying that information that the runtime system would otherwise have about the function. And so that's sort of valuable for, performance reasons.
Yeah, and there is procedure reduce arity, which is a function that does the job that you're talking about missing here. So we could just write, lambda args everywhere and apply, and then call procedure reduce arity at the very end.
Yeah, but it would still need to allocate a list to call to let your function actually run and look at the.
Well, it really is about performance, though.
Yeah,
is the point. The tools are there in the runtime system to get the observable behavior correct, so that all these properties that you can ask about procedures, like does procedure arity includes question mark, for example. There's inefficient ways that you can do that. And so all this code we're going to be looking at is really all about just trying to make tighter wrappers to avoid that stuff.
And I assume that there's just been you spent a long time looking at benchmarks and having people complain, and you figured out all these things.
Yeah, kind of like that, I suppose. Some of it I just sort of made guesses because it seems pretty obvious that you don't want to put a lambda args here. And that was sort of the state of the art until this Popple paper from, I think it was this year or last year, about gradual typing performance came in. And then I had a lot of fodder for very specific things where we'd find that one small piece of the contract 85% of the time of this entire benchmark. And and we could turn 85% of the benchmark into like a 3-line program to optimize in the contract library.
Nice.
So yeah, so there was many of those, actually, surprisingly many.
All right, very good. All right, so enough context. Let's go.
Yeah. Okay. All right. Where should we go? Let's see. Maybe the right thing to do is I think the right thing to do is to go here. So let's start where the thing would start. So this is the macro for arrow. Arrow behaves like a function in the sense that it evaluates its arguments. So it's a macro because it needs to. So going back to the context again, when you write arrow integer, that's essentially what tells the arrow combinator, oh look, there's one. I'm expecting one argument, therefore lambda x is really what we want to write here.
Yep.
Okay, so that's what this macro is about, is sort of finding out what's the shape of the arrow, even though it can't evaluate the arguments it doesn't know what the values of the arguments are going to be. It doesn't know what the domain and range contracts are, but it does know that there's this many of them.
Okay.
And that's the information that it uses to then create those more customized wrappers.
Okay.
Okay, so basically what we're doing here is we're parsing out the domain part. And we'll find out that there's these regular args. So arrow integer will get 1, the integer first there, the first one.
Okay.
There are these keywords are required. There are these keyword arguments that were required. And then let bindings is, as part of the parsing process, it finds sub-expressions inside there, and it collects them into these let bindings, which it then asks you to please put those let bindings outside the full, what you're going to expand into, so that you can duplicate variables without having to worry about duplicating the arguments to the arrow macro itself.
Okay, so that's like when I when I write a predicate right there where it says integer, it doesn't put of the late night projection function.
Right. It's going to let bind that thing because it has to be evaluated. Well, it has to be evaluated early, and then also you want to duplicate the variable gets duplicated, I think.
Yeah. Okay.
So here we're doing these pause obligations thing. The parser for the range part of the contract is just this syntax case expression. So if you write the special keyword any as the result of your contract, then there's no checking at all that happens on the domain, and that can be important sometimes if you care about tail recursion.
It's not that there's. So it is true that there's no checking, but another way of saying it is that your function, the contracted function, is called in tail position.
Correct.
And that's the big deal.
That's the big deal, exactly. So you can't, in particular, the main thing where that goes wrong is that it doesn't check it doesn't check that there's some fixed number of values coming back. Mm-hmm. So if you end with any, that's different than ending with any/c. Any/c will insist that there's exactly one value coming back. That could be anything.
Yeah.
And you can write values and then put a bunch of possibly one range contracts, or you could just write a range contract, not using the word values. And in both of those cases, what ranges will be a list of the contract sub-expressions there.
Mm-hmm. By the way, is this after local expanding, or no? This is just looking at the raw syntax.
No, there's no. It doesn't. Arrow does not call it local expand.
Okay.
It's just going to take the sub expressions and stick them into into this let right here,
mm-hmm.
and then it's just going to build up a big pile of code, which involves those. It basically builds up those wrapper functions and then calls a function, which builds the record.
Okay.
Okay. Yeah. So one last. let's do one thing here. Show you this quickly because that'll help us navigate this code. So this is the expansion of arrow integer. So you see this let,
mm-hmm.
Which was the one we had before, and then it's going to call this record constructor.
Mm-hmm.
And so this is like it's passing along the argument contracts, it's passing along the keyword contracts, of which there aren't any, and it's passing along the range contract, and then it's passing along. This is the chaperone right here. This variable, popular chaperone key ID 16, is bound to this giant function that is the lambda that gets passed to chaperone procedure. That's
okay.
In other words, it's this function right here in blue.
And but it didn't generate it. That there actually is a popular chaperone key.
Yes.
It's just a really common one.
Yeah. Let me. There's a choice in the road here. I can explain that to you, or we can continue to dig into what this lambda expression looks like.
I'll just put that on the stack.
Okay, all right. So in order to get out of the popular keys, I think we have to go to about that many. So if I do this, then we're going to see a slightly different expansion. Okay, so let me scroll back to the top here. This one's not a popular key, as it turned out. Popular. Okay, so, and I should say one word about popularity. Basically, the popularity is the shapes are popular. So an arrow contract with no keywords and one result and 6 arguments, that's a shape. What the keywords are, how many arguments and how many results, that forms a shape.
Okay.
Everything to a shape. And so the case with 6 arguments and 1 result is not considered a popular enough shape to have been pre-built, basically.
Okay.
So you see the same let that we had before with all these integers that are bound, and then these integer 1 through 5 will be sprinkled around various places in here.
Okay.
So here again, we're passing in the list of the contracts to this runtime function that builds the contract record itself. Yep. Here's the keywords again, and there aren't any. Here's the 1 result again. And now instead of a reference to a variable, now we have this giant thing.
Yep.
So actually,
and that's what the macro is going to make.
That's what the macro is going to make, yes. It turns out there's 2 giant things, actually. And we want to skip the first one.
Okay.
First, we want to look at the second one first. So this is the second one. I guess it's not that giant.
It's pretty giant. Now I've seen code that you've written before, Robby, so I know that it doesn't look giant to you, but
I can't tell if that's a compliment or not. All right, so here, this is the function that gets in a bunch of stuff.
Okay.
And then down here, let's see if I can find it in this mess. This function right here is the one that's going to be probably eventually passed to chaperone procedure.
Okay.
So there's a caveat. So make a little asterisk somewhere. We'll come back to sometimes that's not this function.
Okay.
But sometimes it is. And so in the case that it is, this here is now going to be, we're going to integer $!12531 will be the first argument that was passed to this function. And so our job here will be to make sure that integer $!12531 is an integer.
Mm-hmm. And we can kind of see that down at the bottom of the screen there.
Yes. So integer $!125 is the variable that's bound to the late neg. Way. That's the actual projection part of the projection. So you can see it. We got the projection. We've got the actual argument. Yep. 12531, and the neg party gets passed along.
Yep.
Okay. So, and this is being returned in values here. So, and that's like I was talking about before, where the chaperone procedure returns as its multiple values the possibly chaperoned
arguments.
Arguments, exactly. So you'll notice that there's no extra one here for the results.
Mm-hmm. And that's because we're inside of this if that says tail marks match.
Yeah. So this is one of the, this was an optimization that's been around for a long time because this one we knew was obviously important. So, is that if you write a loop that kind of goes through a contract, you'll end up with a mark in the context that has the contract and the blame information. And you can look at that mark and say, I know somebody else is going to check this contract. I don't need to bother with checking the range contract. And because this chaperone interposition procedure is returning 1, 2, 3, 4, 5 results instead of returning 6 results, then the runtime system knows that there's no, that it knows to not put anything in, whatever, to be in tail position with respect to the context.
Yeah.
And so the same thing with this if and the lambda and all these things are all in tail position.
Yeah, and there's a bunch of papers about this tail marks thing, this safe for space and contracts. And I think Dave Herman maybe was the first one that wrote a paper about this.
Right. Exactly. So this is the case where we know that there's a pending check for the range, so we're not going to do the range checking. Mm-hmm. And then in the else branch down here, we don't know that. And so we have to do it. And maybe it's time to go back and look at the code that gets generated.
Okay.
Yeah. So I don't know exactly what's on the stack, but this piece of code up here on the stack is part of an optimization that I think is interesting to look at. And certainly you need to understand if you're going to work on the arrow contract commenter. So we should return to this up pile of code.
Okay, I'll make a note to that.
Okay, at some point. Unless we run out of time, I suppose.
Just for people following along and wondering, where we are in the plan. So Robby sent me a plan before, and we are a little more than half done with this plan.
I'm not sure that's, yeah.
He sent me a list of things, and we are a little more than half through the list.
The list is maybe not all the entries on the list are to take the same amount of time, I think.
Yeah.
But we shall see.
Okay.
All right. So this chaperone constructor, that's that code we were just looking at.
Okay.
And +1 arity function, that's the pile of code that I said let's not look at that yet.
Okay.
So we're calling this function which builds them, and then we're basically returning the beginning of that code we were just looking at in the other window.
Yep. Okay.
So you see the let here, and then here's the call to build simple arrow. So let's look at build simple arrow quickly. So that's going to be something we're sort of used to, hopefully by now. So build simple arrow just calls build arrow. Why does build simple arrow call build arrow and add a couple of falses? Is because those couple of falses get duplicated about 10 gazillion times if you think about the expansion of your distribution that you're downloading.
Seriously, like that makes a difference?
I haven't actually measured it, but build simple arrow, most of the functions that are used as contracts don't have keywords, and actually it's not don't have keywords. I forget what these two falses are, but they're not arrow stars, they're arrows. Uh-huh. And so if you have an arrow star and an arrow both turn into the same runtime representation. Uh-huh. But these, I guess it's like 1, 2, 3 falses and 1, 2, 3 nulls and 2 falses. Yeah, I don't know. I haven't measured whether it makes a difference actually.
Okay.
But the point was to try to avoid having, try to minimize the amount of code that actually gets generated.
Okay, yeah, they're the pre and post condition. That's what the falses are.
Oh, yeah, okay.
The optional arguments.
Yeah, okay, that makes sense. Yep. Arrow does not support pre and post conditions or optional arguments.
Okay.
And arrow star does. So arrow star and arrow are both just different syntaxes that construct the same runtime representation. So they share a stronger function, for example.
Okay.
Which is the reason to do that kind of thing. So what this function is going to do is it's just going to check and make sure, now we're at runtime, and we've got the actual arguments that were passed to arrow, and it's going to make sure that they're contracts. And if they're all contracts, it's going to see if they're all chaperone contracts. And if they're all chaperone contracts, then we know we, too, are a chaperone contract. Mm-hmm. So that's basically what's going on in this code, with the exception of two optimizations. So if all these things hold, then we know that the contract was arrow void. So we don't construct the regular record that corresponds to what arrow void would construct. We just return this guy. This, and the whole point of this is a call to that same make arrow function. So we're passing in all the right things for whatever arrow void needs to pass in. And then this is a specialized function that avoids a few indirect calls in the implementation of arrow void, which if you just call the arrow void contract on void in a tight loop, this is maybe a 3x performance improvement on that program, and maybe a 0.002 performance improvement on any actually interesting program. But arrow void is one. I think it's the most common contract in the if you just do git pull make, you'll have a bunch of Racket code on your file system. I think it's the most common contract in that Racket code.
That's kind of depressing, because that means the only reason that you have arrow void is for mutation and effects.
Yeah. Well, I mean, there's a lot of other things you can do besides effects that all tend to be different from each other.
Yeah. Okay.
Any arrow. So there's a similar kind of a thing here back where arrow void was.
Yeah, I saw for any arrow bool.
Yeah, and any arrow bool actually has a much more valid reason for existing than arrow void. Okay. Arrow void I just did because I'd already done any arrow boolean, and it was so common. So I thought, well, why not?
Okay.
But any arrow Boolean, there are some primitive functions in the runtime system that they get called a lot, and we know that they're always going to return one result, and we know that one result's always going to be a Boolean. And so we can just ask the runtime system, hey, is this a function that's a struct predicate? I'm just not
So
going
it's sort of so it basically like it can turn certain instances of this contract into basically flat ones if they came from the runtime.
Exactly. So that's basically it basically boils down to being able to call this. So being able to call this one function. So it's like a bunch of boilerplate around it that sort of mimics what the contract system is doing, and then this one special case here in line 1516 or 1517.
Mm-hmm. So I mean, presumably it's only useful for struct predicates, but it would also apply to things like number ha and stuff like that. But it doesn't optimize those.
I don't know. Right, it does not. It could. If someone were to implement a function that's basically
does Racket promise is any arrow bool?
Yeah. Struct predicate procedures are what came up in anger. That actually was one of these situations where I boiled down. This is before the whole typed Racket contracts are killing my life extravaganza. Where there was some function where a struct predicate procedures contract was dominating the time of that program. Sorry. And so that's why this got added. And that was some time ago. I don't remember the details anymore.
Okay, cool. All
right. So that's basically, so at that point now, where are we? Let's see.
What the caller of make dash bool.
Yeah, right here. So this is the page back in a little bit. This is the thing that gets, this is the runtime function that gets called when you have an arrow contract, and this is all the junk that it gets passed telling it information about what the actual arguments were, what the subcontracts are, and then it's basically just going to stick it in a record. And that's what's happening down here. This is the record. It creates the arrow record. So you can see it's just highlighting those two characters because that's the struct constructor. Okay. And then these are the pieces of information. And they're basically just the contracts that were supplied as arguments plus those two functions. Yeah. So the chaperone constructor. So the chaperone constructor is going to be a function that takes in all of these other, the ones it cares about of these guys, and then returns the late neg projection.
Okay.
And method ha is a Boolean, and that does the error messages.
Okay. So should we look at look at how it made that chaperone constructor, or are we ready for +1 arity fun? Because I mean, we already saw the expansion of chaperone constructor.
Yeah, I don't know. It's I guess yeah. If you understood everything up to this point, then you could just read that code and probably understand what's going on in there. There's a few special cases that I'm not sure I could just jump to and highlight for people who've already kind of looked at the code and are watching this for posterity. But yeah, I don't know. Maybe we can come back to it if there's still time. There's still some interesting non-obvious stuff in there, but maybe this is more interesting.
Okay, fine with me.
I don't know, what's our time limit here? When are we trying to be done by?
I don't have any time limit. But we normally say that, around 2 hours, we're going to say, let's start thinking about ending it.
Okay.
And so we've got 40 minutes left.
So yeah, so let's go to this +1 arity thing. Okay, so I have to go back, unfortunately, to this window that I know you don't like that much.
Oh, I actually love this window.
Okay. So in order to explain +1 arity functions, I have to, okay, so Matthew pointed out to me at some point along the way that there's really a lot of functions that are first order and they get contracts put on them. And you don't really need a chaperone in the case that you have a first order function that's being called directly in the client. So this next piece of the contract system is really trying to run with that observation.
Okay.
So let me write out a little bit here. So let's say we had, contract out F. something like that.
Okay.
So that's our program. And then in some other module, we've got that.
Okay.
So it'd be really cool if we didn't create that chaperone wrapper around F. And it'd be even better if somehow, and the contract system doesn't do this yet, but it'd be even better if we could basically transform that into something like this. Because then the optimizer would just turn the contract into that, and it would be gone.
Yep.
It
I think that most people, when they first look at contracts, they assume that it does this.
Yeah, it doesn't. If I mean, it can be made to do it. It really, I think we're in a place where it's sort of there's engineering effort and some ingenuity required there, but mostly dollars. So, if you've got a couple of years of programmer dollars burning a hole in your pocket, talk to me.
Okay, so if any racketeers win the lottery, feel free to send Robby some money to make this happen.
Right. And I should point out that there's really a very sad sordid history of people who win the lottery and then get a lot of requests along these lines, and their life kind of sucks after that. So I actually hope that nobody in Racketdom wins the lottery, because all lottery winners, their life is terrible.
I read this horrific Reddit post about this, actually.
Yeah.
Back in January. All right, so let's go on.
Okay, so it doesn't quite turn into that.
Okay.
But what it gets kind of close to that. So what we get on the server side is we get this other function. It looks like this. Okay, something like that, where inside here, and again, we're going to do this thing. Inside here, we have the checking. And now remember this, so this is on the server.
And because it's on the server, it's exposed to optimization?
No,
okay.
But there's only one of them, and it doesn't know that thing. It doesn't know this green thing.
Okay.
So it doesn't have the name of the neg party. So the value of it being on the server is there's only one of them.
Okay. Okay, yeah. Allocation.
Right? Yeah. So we made only one of these F2s, basically.
Okay.
So, and the value, and the downside of being on the server is we don't know what the neg party is. And so, we have to, we're going to want to do checking here in this ellipsis to make sure that X is okay before we get to line 18. And that checking is going to involve, else branches where we're signaling contract violations, and those have to have the neg party.
Okay.
Right. So, so this is the function that gets created by contract out. So contract out says, oh, look, I know arrow. So if you had written this, which is a totally legitimate thing you can write, values just returns its argument, that will work. It will do the same contract checking. Contract out won't be smart enough to notice that you've done that and won't invoke this optimization that we're talking about. So contract out just actually looks at this and goes, oh, look, I see an arrow. Therefore, I know I want to create this F2 function.
It won't even work if I put in an empty let binding area?
Right.
Ooh. So this is kind of like a violation of the macro writer's Bill of Rights.
That's right.
Okay, go on.
Yep. There's a whole other, we should, that would also be cool,
Yeah.
If this mythical lottery winner wants to, et cetera. Okay, so that's what's going to show up on the server in this case. And then on the client, we're going to transform that F of 3 into F2. Client's name goes here.
Yep.
3. And the 3 is just because it was a 3. So whatever expression we had is what expression goes there. And because this was an F, then so in order for this to work, what actually gets exported, F is not exported directly. It's this macro that says, oh, am I in an expression position? Am I
should I be F2 or should I be F?
Yeah, exactly. So it's define syntax F and then says something like, here.
So maybe
am I an identifier?
Yeah, so maybe an example, if we go back up to line 11 and we add another thing where you said list F, Or yeah,
So
or
if you
even
did
that.
this, for example, or if you had done something like this,
Yeah,
you would defeat the
I'm just trying to
optimization.
think of things that are actually useful. You know, like storing f as in like a data structure.
Oh yeah. Yep. Yep. You store f in a data structure. Anything that basically, so if it doesn't see this open paren essentially right before the f, then the optimization sort of begs off.
Okay.
Okay. So that basically all this this other function which we scrolled past before is all supporting this optimization.
Does it check the arity?
Yeah. Yep. So if you'd written that, then we would fall back. It would create the chaperone. It would do
Oh,
all that
really? It
stuff.
would create the chaperone. It doesn't like expand into raise blame.
Why would it? I mean, who cares? Your program's going to crash anyway. It's going to be fast.
Okay.
We can crash quickly, no problem. The real worry is not that we see f of 3. The real worry is we see something like this.
Mm-hmm.
Whatever. Hello. I typed a very large number, and Dr. Racket is now thinking about it. Sorry, probably shouldn't have done that. Okay.
All right. Okay. So this whole thing is called the +1 arity function because it creates f2, which is a function with the same arity +1.
Exactly.
Okay.
All right. Oh, I see. I typed square bracket instead of 1. That's why it was taking so long. All right. Anyway, this is the kind of thing we're worried about. Sort of the moral equivalent of that program.
Uh-huh.
All right.
Okay.
Okay. So that's the basic plan for what we want to do.
Okay.
And now I think we have to go here. Okay, so actually this file, arrowval first, it really doesn't contain what does it contain?
Well, I know that arrow higher order is the thing that actually makes chaperone procedure.
Yeah, arrow higher order is the one that builds that chaperone function we spent however long talking about. But I think I've forgotten now exactly. This is one of the nice things about being able to do this is I sort of lose track of which things are in which files.
Mm-hmm.
But anyway, so here's this. Right. While we're talking about this, let's. Okay, since we're about to go through this code, let me also explain. Remember when we did expand with arrow integer, and we got a much smaller thing than if we did expand with arrow and 6 integer?
The popular keys.
Yeah, the popular keys. So let me explain the popular, because we're going to have to go through that code on our way to the construction of these +1 arity functions.
Okay.
So that's this guy. So build +1 arity function plus chaperone constructor is a function that takes in essentially the shape of the arrow contract as specified for all these arguments here.
Okay.
And then returns the syntax for the chaperone creation function and the +1 arity creation function.
Okay.
And it does this by looking up in this table of popular keys. So let's look at this table. So these are the popular keys. So let's see, I'm forgetting exactly which one of these things is which, but this is basically saying no arguments, no results, no keywords, returns 1 value. No arguments, I don't care what the results are, so arrow any, and no keyword arguments.
Okay.
So these are all basically just the shapes. Okay, and so these then get turned into calls to the functions that build the chaperone constructor and build the +1 arity function, and then they get defined at the top level of arrowval first.
Okay.
So that variable that we saw, if I can look at this.
This is probably too involved in a question, but I'm just deeply curious about what the impact of adding another thing there or removing one is.
Somebody has to write some more code, I guess. What do you mean? Where did I go? You mean adding another thing here?
Yeah, so if I add another line there, more code, like the ZO for this file will be bigger.
Sorry, misunderstood your question. Yeah.
And constructing an arrow will take longer slightly you know?
No,
So,
it's
like,
really all about avoiding making ZO files bigger.
yeah, so I wonder, like, what is the function? You know what I mean? Like, I want to see a graph of as popular keys gets bigger, the size of zeros gets smaller, and we basically look at like when the derivative of that like goes below a certain point.
Yep. Yeah, that we could do that. That's an experiment one could conduct.
Yeah,
I
but
mean, you really want to look at that. You know, what's the best point in that spot over time? I suppose.
Yeah.
Right. Yeah. So this has changed, I think, 2 or 3 times now in the history of since this code existed, as our distribution has changed and whatnot.
Cool. I like it that they're not you know, actually pre-programmed. It just I can feel beauty coming from this file.
Thank you. All right.
Okay.
Okay. Yeah. So right. So this here.
So what's special about these? Does it really just call the same function?
Yeah.
It calls it statically and saves the result.
It calls it a compile time of arrow val first instead of compile time of the use of arrow.
But they're literally the same function.
Yeah. Yeah.
Okay,
it just takes this like list of things and turns it into arguments.
Okay, cool.
Yeah. So we could probably, yeah. So, let me see if I find the right one. So build +1 arity function, blah, etc. This is the function that's going to look in the table to see if we've already built it, in which case it'll return an identifier, or it's going to actually build it, in which case we'll return a giant pile of syntax.
Yep.
And here's the check that says, is this key in the list of keys? And in which case we return, and this will be 2 identifiers.
Okay.
And this is the function that we want to, this is the function we're heading to look at. And it's actually let's see, it's going to be called, apparently it exists in this file. It's referenced in this file 3 times. So here's the call for the case when we're not in the popular keys.
Yep.
And what is this case? This is, I think, the
for
case.
The popular ones.
Yeah, so this build populars is this macro that then calls that function.
Yep.
With all the things that are in the popular keys, and then the third occurrence of it is the function itself.
Yep. Okay, cool.
Yep. Okay, so here we are. So here's the shape information coming in as all these arguments. We set up a bunch of variables. Yeah, I don't know. This is, yeah, I'm not sure what's the right order to think about reading, but we're basically building up all the little pieces that go into any possible one of these guys.
And so what's the trick? Like, are there tricks, or is it just hard work? Like, or is there things that are not obvious?
I don't know that there's any tricks. I mean, the whole thing seems pretty obvious.
Okay.
You know, if you've lived in my head for the last 20 years that I've been hacking on this, or whatever, 15 maybe.
Okay. There's just a lot of things to keep track of. The optional arguments, the optional keywords, the mandatory ones, whether there's multiple values, things like that.
Yes. In fact, that's more evident in Chaperone constructor code, I think, than it is here. But the really the way that if you want to modify or maintain or do something with this file, you really want to heavily, deeply rely on the about, I don't know, what is it, some number of thousands of unit tests for arrow. Yeah, it's very easy to okay. So yeah, it's very easy to make mistakes and that are just dumb little mistakes, and what you forget about some special case that you have to also handle.
Okay, so maybe it would be useful to see where it tells whether or not it's allowed to use this +1 arity function.
Oh yeah, sure. Let me just there is something that well, let's see, what are these? So we've covered a little bit of these issues before when I wrote that case slam down. Okay, so let's see. If you're reading through this and thinking about making changes to it or extending it in some way, the main things to keep in mind, I think, are that when you call chaperone procedure, you have to supply a function that has just as many, just as large an arity as the function you're passing to chaperone procedure. Yep. But that function you're passing to chaperone procedure might have a larger arity than what the contract allows. So if your contract is arrow integer integer, and your function is actually lambda args, blah blah blah, then you have to make a lambda args to pass to chaperone procedure. You can't pass lambda x. Right. So that's one issue, and
that makes sense because of the chaperone rules, but it's surprising.
Yes, exactly. And it's also, I believe, I don't think I've actually, excuse me, I don't think I've gotten the statistics on this one, but I believe that that's not an uncommon case, and certainly it's not. It's one of the cases where we fall back to not doing a particularly performant job in the contract system. So it'll make this kind of efficient wrapper. It'll sort of hope that you are, when you have an arrow integer function, going to supply something whose procedure arity is just one and not something that includes more than that. And then we'll do a dynamic check on the function and determine that the arity is not that simple well-matched arity, and then it will, so I think that might even be open still over here in this file. It's this guy here, arity checking wrapper. Yeah, so arity checking wrapper will. That's in this file. It's this function. So that's what this is doing. If the arity matches exactly, and the keyword arity matches exactly, then we're going to return one of these n functions that, maybe we should look into this a little bit more. I don't know.
Okay.
Okay, I could probably just tell you. So there's a lot of options here. So basic lambda is the one that you've been thinking of this whole time, that gets passed to chaperone procedure.
Okay.
Then we sometimes use
you mentioned this, by the way. You said back when we first saw this, you said sometimes a different function is called than the one generated by arrow, and this is what you're talking about. Yeah,
exactly. Exactly. So basic lambda is that one that you think of, the one that I wrote out the example. Yep. And then sometimes we use unsafe procedure chaperone. And what unsafe procedure chaperone does is it doesn't do the chaperoning checks. So it says, yes, this is a chaperone, but it doesn't actually make sure that you just supply an arbitrary wrapper and you get to pretend that you're a chaperone. And so those can be more efficient in some cases.
Okay.
This result value is assumed. The runtime system knows about some procedures that they are guaranteed to return a certain number of results.
Okay.
So you can say procedure result, I think it's procedure results arity or something like that, is a function, and you give it a procedure and it will either say, I don't know, or it'll say 1. I think
okay, and so this is like those struct accessors.
Yeah, exactly. So the information is coming from a different source, but basically there's a little bit of information on the procedure record at runtime that can say that the compiler determined that this procedure is guaranteed to always return exactly one result or not return at all. And in that case,
this matters because we don't need to make the case lambda.
Yes.
And exactly. A case lambda is inefficient.
And we don't have to use call with values. We can just say let.
So there's all sorts of reasons to like that.
Exactly.
Okay.
This no tail is a situation where we've determined that the procedure that's got the chaperone on it, or the procedure that's going to be contracted, is kind of simple enough. And what's simple enough, what we really care about with simple enough, is that it's not involved in a loop. It's not, if I call it, it's not going to go off and loop out to some other unknown place. And in that case, we don't have to put the tail checking. We don't have to do that tail checking code that we saw earlier.
Yep.
Okay. So that's what those 4 functions are. So those are the 4 possibilities, and we're going to look at the function and see whether it matches them and then use the appropriate one.
Okay.
It seems to a thunderstorm seems to have started here. So that's what that is in the background there. And then in the case that the arity doesn't match exactly, we basically fall back on this lambda args thing. And where's that'll be in here somewhere. So we check to make sure that the arity is allowed and signal various errors. And then if it isn't allowed, we make this kind of dynamic low-tech wrapper function that what it does is it gets in all the arguments, makes sure that the arity is appropriate based on the contract.
Yep.
And then makes the call into the other function. So kind of inefficient twice in that we're creating these lists multiple times. If it was a lambda args function, which has got the arrow integer contract, we're gonna kind of create that list twice, once in the wrapper and then once in the actual function itself.
Okay.
And yeah, so that's what's going on there. That's what that comment was about. And these guys right here are that was the other main thing I was thinking about. And we've covered tail wrapping. And yeah, I think that's
okay.
I think that's most of what's going on in Arrow.
Okay, and we were going to go back to how we can tell that we're allowed to use the +1 arity function.
Yeah. Where is that? Oh, right. Okay, so that's in this file, I think. Yeah. Okay. So that's in contract out. Contract out. Okay.
You mentioned this before because contract out is going to see that it's an arrow and then do something different.
That's right. So contract out is the one, you're going back over here. Contract out is the one that has F. Nobody else has F.
Mm-hmm.
Right. So that's the one that's kind of making the connection between the arrow here and this call in the client module.
Okay.
So that's why the code is there. And that's why this. At some point, I realized I should really do this for define/contract2, but I don't remember if I actually did it. So in principle, it applies to define/contract2. And I believe that typed Racket takes a slightly different path. It doesn't actually call contract out directly in its expansion, but it calls into, I forget exactly how that works, but it calls into one of the helper functions inside this library here.
I see.
And I'm forgetting how this works exactly. So no luck there. Oh yeah, this is it actually. All right. So yeah. So this guy is the transformer, and it has this I am a transformer property.
When you say the transformer, you mean the macro, the F macro that gets generated.
Yep. Okay. Yep. So we're going to bind this instance of this compile time, and then this is what gets called in the client side at the reference to F.
Okay.
Okay. And all this complexity here is dealing with something else entirely. All right, and let me explain what that something else entirely is. So what if we had?
I feel like that is the motto of this code. This complexity here is dealing with something else.
So imagine this was the client now. The lines 11 and 13 are the client.
Uh-huh.
You don't want to create two chaperones.
But there's just one F2.
Well, never mind. Let's yeah, sorry. It's not even that.
Oh, so this is like list FF.
Yeah. List FF. There we go. Let's say we saw list FF. List FF. So let's say this was the program, the client side.
Yep.
You don't want to create the chaperone wrapper for F twice.
Yep.
You have to create the chaperone wrapper once per client because the client has the name of the client knows its name, and the chaperone wrappers will be different for every client, and that's part of the wrapper. So it has to be different. You have to have at least one per client, but you don't want to have two per client just because there are two references to F.
Yeah. So just going all the way back to talking about projections in the first place, a big part of organizing it that way was to not have so many allocations. And so we're basically saying at every point that you can share representations, do it.
Exactly. So it'll do something like this. But this is what the transformer is going to do. It's going to turn list FF into something like that.
Okay.
And
So hold on. So I would have expected, and maybe this is what you meant, it would have turned it into, F2, it's going to say define F2, and then it's going to say F3 neg party, like me. Because like
no.
the code between 12 and 14 only needs to be made once per server.
No. The code between this thing in the ellipses here is okay. So this is really actually we saw the name for this earlier. I can never remember. It's something like build chaperone procedure, right?
Yeah, and so this is concerning to me because that means that the clients have this big chunk of code rather than just
I don't know what client's name goes here.
Yep.
Yeah, but I mean they have.
It's not that much. It's not that big.
You're right. You're right. Actually, the actual call to chaperone procedure is not here. The actual call to chaperone procedure is actually, I think, inside arrowval first.
Mm-hmm.
But it's something like,
build F chaperone.
Yeah, build F chaperone. So it's
okay. Like yes. Okay. Yeah, I'm good with this then. Never mind.
Yeah, that's actually what it is.
Okay.
Actually,
sorry.
we're just looking at the code that calls chaperone procedure. Actually.
Okay. All right. So the same code that tells whether to use the +1 arity function also will generate this top-level definition inside of a client.
That's right. And that's what we're looking at right here is that piece.
Okay.
So yeah, I didn't look through this in preparation for our discussion here, so I'm probably not going to go in the best order. But
okay.
Maybe I'll recognize the code when I see it. So maybe I'll be able to. That'd be a good thing. But really, okay. So what's going on here is we're building up this table that maps from basically some identifier that describes what a module is.
Yep.
So am I in the same module or not? To go back to this file to F2.
Mm-hmm.
So that's what I think that's what saved ho ID table is.
Yep.
Is that? And here we have both of them actually. So I think these two partially applied ID is going to be F. Maybe I shouldn't have called these both F2. This is going to be this F2 as opposed to the F2 over here. So let's maybe call
this. Let's just name them F3.
All right. Yep. So this will be F3, and this guy is going to be F2, I believe.
Okay.
And so there's various checks right here that make sure that we're actually inside a module, and sort of we're in kind of a same place where we can lift something out to the top level. We have that capability.
Yep.
And then if we can, then it either lifts it out to the top level or uses the one that already has been lifted out to the top level. So that's basically what this code is doing right here. Mm-hmm. And gen slow path code is the code that does the F3 call as opposed to the F2 call.
Okay. It says right there, syntax local lift expression to figure out what it is, or it looks up in the hash table. Yeah, okay, I see it.
Yeah, exactly. And then, okay, so here we are. This is STX. We're hoping STX is going to be something like open paren F and the right number of arguments.
Yep.
So if it's just the identifier, then we know we're in the case like that F3 that we wrote. We know that it's like this list F3.
Yep.
So we generate the slow path code. If it's a set bang, that's a syntax error. You can't set bang contract out variables.
Yep.
If it's now we're in the case that it might be an application of the right arity. So we check to see whether this this expression here is it had the right arity. So this is the thing you were asking about earlier.
Yeah.
So valid argument list, it basically collected some information from the arrow contract, the syntax of the arrow contract, to know what are the right keywords we're looking for, if keywords are supported. I can't remember what the right arities are. And so in this case, then we know in the case that we get true back from that function, we know that we can expand directly into the F2 function.
And we really need to do this because the F2 function only checks the values, not their arity.
Right. And we don't care to not, we hold valid argument list returns false. We sort of don't care. We're not interested in performance anymore because we know we're going to crash.
Yep.
And
it'd be nice to, put in some sort of syntax information there so that some tool that Vincent makes can say, I can tell that this is going to crash.
Yeah, totally.
Could you put a comment there?
Actually, Dan is the person here.
Yeah, Dan. This code will crash.
Make sure your analysis finds this guy. Yeah.
Yeah, cool.
Okay, so, right. So I can't really remember what these are, but this should basically turn into F2, that expression. Here's the name of the client, and then more is just whatever was there.
Yeah, whatever the arguments were.
Whatever the arguments were. This piece here is one of those cases where we sort of weren't, it wasn't a good time for us. We didn't know. So you know how macro expansion, if you're in a definition context, it kind of does this 2-pass thing. Yeah. So that's sort of coping with that timing, with those timing issues here. So if we're in that kind of first pass, then we can just expand it a #% expression to signal that in fact this is not going to define a variable any names, and then and then we'll end up back in the good code here in the second go.
Although it does define names, but it only defines with syntax local lift expression, so nobody else can find out about them. So the definition context doesn't care.
Right.
Okay.
Right. So how this thing actually gets stuck on F itself in the server module's exported version of F is probably somewhere. But
I'm sure it's somewhere.
It's this make provide arrow contract transformer, which is here we are. So here's that predicate you don't like, or that was not that you didn't like it, but as you observed violates the macro writer's bill of rights.
Yeah.
So this arrow, this is in the this function was part of the refactoring I did in order to make type Racket happy, and I never found a good name for it.
No, I think that's a great name. I think I like all your names. It just says so much about what it does.
The name is accurate, I have to say. It has that going for it. So essentially, what's going on here is it says, is this a function contract that I am willing to invoke the optimization with because I know it's well behaved.
Mm-hmm.
So you see it's supported for arrow, arrow star, and arrow I in certain cases. And this valid app shape code is combined with the code that does the checking for the call site that we just saw a moment ago.
Yep.
To see whether those two match up with each other. So they're together, those two things.
Okay.
And then so if we did find something that we know is to be an arrow, then we also learned what the valid shapes are going to be for the application sites of functions that match that contract. And so we get both of those pieces of information out of there. And then if it's an arrow, then we're going to contract out is going to expand that F to this is the constructor for that for that record we saw earlier. And this is the reason why we make that record anyway, is to be able to hold on to this partially applied identifier, which is partially applied identifier. This is partially applied in the sense of it's a latent egg projection, which has had some of the things. It's got the blame object already, basically.
Cool. Well, so you might not realize this, but we're actually done with your list of things that you said you wanted to talk about.
Awesome.
So, what are the cool parts of the contract system that you didn't get to talk about today? I can think of like two in my head. Like I think that the lazy data structures must be very neat, and the whole test case generation contract exercising is probably very interesting as well.
Yeah, they were fun to implement. That's for sure. I don't know. Arrow I has got some fun stuff in it too, I think. So
yeah, and the whole, the whole distinction between all the various kinds of ROI that have happened over the world, like over the experience with the Racket contract system.
yeah. Although I would say don't look at the old ones because they're kind of shameful. But I'll tell you, since we talked about, well, lazy data structures we didn't talk about, but I'll tell you just two things about ROI that might, that are worth probably passing on. So when ROI, the syntax is different. You give names to the variables. So it looks like arrow, except for there's like an extra pair of parentheses and identifiers that name the arguments.
Yep.
It looks like arrow star, actually. So we could say something like this. This is the way that you would. That might be a contract for the less than function or something like that.
Yep.
And you can say, well, I really want X, the contract on X, to depend on the value of Y. And then you can say something like this. But now this is saying that the function accepts two arguments. One of them has to be an integer, and the other one has to be smaller. So the first one has to be smaller than the second one.
Yeah. This almost has a feel. The syntax always reminds me of let rec.
Yeah, that's right.
The let rec. You know what I mean?
Yes.
Yeah.
Yep. Which is kind of one of the things that was where I was heading with this, is that there is this kind of issue with circular dependencies. So if you write this, it tells you ROI generation of X's contract depends on X's value, and then it like the part that's elided here is the path.
Yeah.
The fact that there's a cycle in that path. So
yeah, it's cool that it figures that out.
And so there's like a little topological sort inside there, where this will be okay. Where it has to figure out what order to evaluate these expressions in.
Yeah.
And it really wants to go left to right. But when if you write a contract like this, it has to go right to left, because it doesn't actually, you need the value of Y before you can figure out what X's contract is.
Yep.
So it's going to actually check Y's value as an integer before it evaluates that thing. That's one piece of if you're looking through the code, you'll find that I copied, some algorithm from Wikipedia in there to do this topological sort, because of course I don't get the topological sort library in the contract library's implementation.
Yep.
Right. That's one thing. And then the other, I forgot the other thing. Oh yes. Here's the other interesting thing you could do is you could, let's say that Y wasn't integer, but was a function on integers. So let's call it F. Now, what happens with this program?
Who's at fault?
Yeah, exactly. Well, it's like the contracting itself, right? So that was Christos's work, sort of figuring that out, and that's one of the reasons why you don't want to look at the old versions of ROI in the contract library, is because they get this all wrong.
And so the naive thing is that, oh, well, obviously it's the positive side because the positive side provided this function, but that's not quite right because the contract was made someplace and then it could be attached to something later. So there's really three people involved.
Exactly. So the contracts of
the third
a party
are the same.
Exactly. The contract itself becomes a party to this, to itself somehow. So this one should say, this is a screwed up contract. It shouldn't say that one of the two parties to the contract has gone wrong. And this is what happens. It's code. Contracts are code, right? That's an important thing. We shouldn't forget about them. I mean, types are code in a sense, but they're like code that's better than us. Contracts are code that's as good as we are. It is.
There's this trustedness to types that you trust.
Well, I don't know if it's the right way, but the point is that the contracts don't have that. Contracts are really just code in the same way everything is code, and you can write whatever program you want that computes whatever contract you want, and you can drop it right in where I've written f of false. And of course, like any other code that you write, it can have errors.
It probably does have errors.
Okay. So somehow the contract itself is now being a party where there can be things have gone wrong, and you and I, if we agree to live by some bogus contract, that's somehow a different kind of error than us agreeing to a contract that makes sense, but then not living up to the contract.
Yeah, totally. Okay. So, so the next thing I wanted to ask you about is, like, what is next for the contract system? So, as we were going through here, we were like, oh, wouldn't it be great if we could do this? Wouldn't it be great if we could do that? I mean, are these just wishes? Are they planned? Are there more important things that are planned that you didn't get to talk about?
Those are mostly wishes. I have a lot of wishes. I don't know, but the one thing that's actually something close to a plan is doing a better job with avoiding redundant contract checking.
Yep.
So this comes up in the case of typed Racket, where when you go back and forth, you have all these boundaries between typed and untyped code that are maybe not super obvious to the programmer. You don't want to be thinking about them. Certainly, you want to just port your program as you go. And so different subsets of it are going to be in typed and untyped, and every time you're crossing back and forth, you have another boundary there. And so you can end up with the same contract being checked lots of times.
Yeah, and there's almost an analog here to Redux, which does the same thing, but its solution is to just make this giant cache hash table, which doesn't seem to be probably a good idea for the contract system to do that.
Right. So it's basically starting where Contract Stronger started, and then doing a better job, a more comprehensive job with something like Contract Stronger.
Okay.
And there's more to talk about there, obviously, but we have some benchmarks from typed Racket where contracts are piling up, and in fact, there's even an old benchmark from an kind of from an OO, sort of an OO style, where you can write this with just functions, where sort of roughly every time around the loop you double the number of contracts that are put on a particular function.
Okay.
And so you see, exponential growth in the number of iterations of some loop in the running time of your program. Very, very bad. To have I'd sort of thought about this problem before, and I'd never realized that there was a way to make it worse than polynomial blow up in the number of redundant contract wrappings.
Yeah, that does. Anytime that the library or implementation or something like changes the asymptotic complexity of your code, that's really a sign that something bad is happening.
Yep.
Okay.
So there's plans afoot to try and do a better job with that.
Mm-hmm. And then kind of the other dimension of things that could be done in the future is like just, implementing more varieties of contracts for more exotic data types. Do you have any thoughts about what's possible or not possible there?
I don't know. I don't have any immediate plans for things like that.
But like,
I'm not sure where you're going.
As an expert in this, like, going back to what I mentioned before, there's sort of this idea that anything that a static type could do, we would like to be able to make a contract that can do the same thing.
Yeah.
I feel like that is a kind of roadmap. Like, how do you feel about that? And do you feel like there are certain static types that are, implausible or not worth going off and checking?
I think that roadmap is relatively well explored, actually, in the contract system, and it seems to be relatively well explored in the research landscape too, to the point that I'm not sure how much more value we're going to get out of squeezing that. Really, I don't know.
And are there things like in the research landscape that like people have done theoretically that we've never actually implemented in Racket usefully?
With respect to contracts and I think the main thing I see there is really doing a better job with the redundant contract checking, where we have some ideas about how people have done that, and then there are people who've built calculi that have properties like they guarantee that there is no growth due to contract checking.
Yeah,
like Michael Greenberg has a paper. Yeah. So I don't think we'll be able to get there because in an actual implementation, because you have to be able to decide undecidable problems to tell whether or not two contracts are equivalent. But I
Mhm.
think we should be able to get there for any reasonable program. Yeah.
Cool.
Yeah, there's I don't know. I think really the best advice, the best answer to give here, which is totally a crappy answer for somebody who's actually listening, but is like Christos is the main author on an ICFP paper this year that explores these issues kind of related to this, like where should we go with contracts, what's the right way to think about them,
Yep.
kind of lays out how we've been thinking about them, which has taken a long time to crystallize,
Yep.
and going forward with it. And really that's the listen to me blather on is not going to be as good as reading that essay, because Matthias did a hell of a job writing that up. So.
All right, cool. Well, I had a lot of fun digging into this code, and I'm very grateful for you giving us a tour of it. Anything else you want to end with?
Thanks very much, Jay. I love that you do these. I've been listening to all of them, and it's been great to participate in one.
Cool. Well, I will email out this to the mailing list. Oh, one last thing I forgot to ask is, are you currently using head? Like the code are we looking at? Like what revision are we looking at? Just for posterity's sake.
Yeah, we're looking at head.
Okay, so when I link it on the wiki, I will link to this current version. So thank you again, Robby. We'll see you soon.
Okay,
Bye.
Thanks, Jay. Bye.